So here we will introduce the radiomics, which is a machine learning approach to medical image analysis. I wasn't sure about whether to talk about that also this year because it's a bit fading out of fashion, but I think it's very didactic, so we will spend half an hour of the course on that because I think it's useful. Now, first, let's refresh and go a bit more in depth about the concept of pattern. What is a pattern? A pattern is a regularity in the world, in a human design, or in some ideas. And so this is a classic example of a pattern in an image. And the question is, why do we care? Because if I ask you what is this, probably you have no idea, rightly so. Now, if I ask you what this is, and this is not even a proper picture, this is a blend between a picture and a cartoon that I did myself, and I ask you what it is, can you guess that? Yes. Indeed, it's a wall, but actually it is two gray rectangles and some two gray big rectangles and some lines that I draw almost myself. But your brain recognizes that it says, okay, if you have this kind of regularity and that kind of shape put that way, and these are offset by like half a brick, probably that's a wall. And if I show you this, I don't know if you can see well enough, you probably can see on top of the smaller rectangles, there is some coarseness on top of that. And so you might say, okay, this is probably they are trying to replicate the stone look, bricks made of stones and not by clay. So patterns really convey a lot of information. Now, let's introduce the concept of biomarker. A biomarker is defined as a measurable indicator of some biological state or condition. Generally, we talk about blood or fluid samples. When you're doing your blood tests, you get cholesterol levels, glucose levels, and 10 pages of serum levels. And this is the most classic example of biomarker. You measure that, and it indicates some states or condition, not necessarily pathology. Some are maybe like if you have elevated glucose level, that's a symptom, it's not a pathology. It can be a symptom of 20 different conditions, but it's an indicator. The question in our course is, can we get a biomarker from images? Because as I told you until now, the images are read qualitatively from humans that have spent years in learning, in training their brain, like it was a neural network, to spot some recurring patterns with all the limitations that come from that, because our brain is super good at learning patterns. So if there are no patterns, it likes to make patterns up itself, which is not very reproducible in medicine. The concept of radiomics is this kind of pipeline. So you first need to define a number of descriptors of an image, which, as you guess, is pretty complex. Then you need to identify the relevant ones amongst all the possible descriptors. And finally, you just do what probably as data scientists you did already hundreds of times in the most different fields. You feed all the numbers that you have in some classifier or regressor. The question is, how do you quantify an image? And it's non-trivial, absolutely non-trivial. They have come up with the concept of feature. And you have, and when they introduced the features, you had, they also came up with the concept of order of features. The first order is called the zero order, and it's pretty easy. You spot somehow something, an object in an image, you define its contour, and then you can describe its shape. How do you describe a shape? Again, that's non-super trivial, but you can have some trivial indicators like area or volume if it's 3D, the surface if it's 3D, and then you can compute the surface to volume ratio, the diameter, maybe the sphericity if you have the perimeter, the surface, and the volume of an object, if given how the ratio it is, if it's very elongated, very circular, it probably makes a difference. Then you have a first order feature. Again, you have already identified your object inside the image, and then you take the histogram of all the intensity values within that area. It will be a distribution. It's not a spatial distribution, it's just an histogram. And from that histogram, you can get minimum, maximum, mean, median, and then all the other descriptors, kurtosis, skewness, which all might have some meaning. If an area image is spatially uniform, then probably the mean is very close. The standard deviation is very small compared to the mean. There is no tails. There are no tails in the intensity distribution and things like that. If there are, if it's something very black with some very bright spots, probably the kurtosis and the skewness tell you something. And so it can all describe what you're seeing somehow. Then you start describing patterns, which are texture. These are things that we humans are pretty good at describing with words, but it's pretty hard to describe them mathematically. We can talk about the patchiness, if something looks patchy, if there is some graininess which might be coarse or fine, some noisiness, if there are some string-like patterns or things like that. It's like fibrosis in the heart after a myocardial infarction. In some MR sequences, it looks like an area full of string-like patterns. So there is some meaning to all of that. So I will try to give you, I will give you an example of the simplest descriptor of texture. This is the first one that was invented. It was invented already in 1973 by Haralick to analyze satellite images. And it used this co-occurrence matrix to recognize automatically if an image of an area was built, grassland, rocks, or things like that. Apparently, this was effective enough for what it needed to do. The question is, given a pixel at the gray level, x, how often does the next pixel have one other specific value? So suppose you have this image, this 4x4 image. And we have the intensity. So if we have intensity 1, how often the pixel on the right has intensity 1? Not here, not here, not here, not here. So 0 times. How often, if we have intensity 1, we have intensity 2 on the right? 1, 2, 3. So we put 3 here. And you fill one so-called co-occurrence matrix this way. And I said, let's take a look at the pixel on the right. Why the right and not on the left? You can do it also on the left, and you get matrix C. And so in this way, you got some concurrence matrix. You can go further and have it on the left, on up, down, in 3D, and so on. indeed, this is just a small extract of his 73 paper, and it says that texture can be fine, coarse, smooth, rippled, molded, irregular, lineated. It gives example of his own applications. And here it says the important thing, texture is an innate property of virtually all surfaces. It's an important thing. Let's give you an example of how the co-occurrence works. Here we have a fully random noise. If you compute the co-occurrence matrix of that, we see things like that. Generally, every pixel has another intensity which is non-correlated. But if we have some blobby noise, a blobby structure, we can see that if one pixel has a certain gray level, the next one will have most likely the same noise level. So this will be almost diagonal. This is a kind of correlation if you think about that. Once you have these matrices, what do? You can compute statistics on the matrices. So from one matrix, we already got into multiple descriptors. There are a number of factors that influence that. So we have said one factor that influences that is the spatial scale. We said, let's look how often the next pixel has a certain intensity level, but why the next one? There is no reason. So maybe you should say a pixel X millimeters away if you're working in images, X kilometers away if you're working on satellite imaging. And in our case of the blobby image, if instead of looking at the next pixel, you look at 3 pixels away, you see that there is almost no correlation. These blobs have radius of about 3 pixels, so that's it. This is also influenced by just how big is the matrix. If you have many more pixels on which to compute this parameter, the numbers will be higher. And many indicators that you compute will be influenced by that. Then, I haven't mentioned that until now, I've hidden it to you, but how many gray levels? If you have, we said that on images that we display on screens, we have 256 levels of gray. But if we do this computation on 256 levels, this matrix will be 226 times 226, and it will be mostly empty, and with a couple of points here and there which we cannot interpret. But at the other end of the spectrum, if we discretize our image using only 4 levels, we don't have any resolution to see anything. Now, there was, when this field was starting to become popular, they started a very big collaboration on standardizing all of these indicators, and they invented not only the co-occurrence matrix, on which they computed 25 indicators. And each of these 25 indicators could have been computed with different noise levels, different discretization levels at different numbers of pixels away, and so on and so on. But there were other matrices and so on. So it's, it's interesting didactically, but it's not really a stable way to analyze images. Now let's see the typical analysis pipeline. You had to identify the regions over which to extract features. You generally use the human segmentation. Then you extract some features, which can be potentially infinite, because you have, even in the standardized version, you had some 200 features, and all of them you could, and all of them can be computed with a number of hyperparameters that can be varied. Then you need to remove you can remove all the unreliable features. That's something you can do in an uncrafted way. you can perform a study to see if some features describe factors that you're not interested in. Like you can add some noise similar to the acquisition noise, and if you see that some features describe your noise, you say, okay, they're not describing a biological factors, and you remove them. Then you can remove redundant features, like like you do in many classification tasks. And finally, you feed what you found in your classifiers or regressor. Now, even after the advent of popular neural networks, there was a group of people which was saying that this kind of analysis could have been very interesting due to the potential explainability of this method. However, it's a very tricky question because if you are working with the ones that I've called zero order or first order features, at least some of them, like the shape, the area, you say, okay, two more small, bad, good, two more large, bad, which is not the case for pathologists, but whatever. These, of course, make sense, or bright spot versus cold spot, two different cases. That makes some sense, but when you go to, if you get 1,000 features extracted, then you feed them into a random forest, I wouldn't really say that this is more interpretable than a neural network. For me, it's not interpretable at all anyway, especially considering how removed the entropy of the co-occurrence matrix is from the appearance of the image itself. So, you know, explainable artificial intelligence is a big topic. It's also a requirement in the European Union for critical artificial intelligence systems, but I wouldn't say that this way of proceeding really solves your problem. So that's it for radiomics, and if you go to what you see, if you go in our repository, okay, you're seeing that. You will get a Jupyter notebook about an experiment to run with radiomics, which is, I've chosen a case, I've given you a task where it's pretty nice that the radiomic classifier works, because it was tried in thousands of cases, and radiomic also gave some confounding results, but in this case, I ask you to familiarize yourself with the data set, be able to read that, able to read the segmentation, and now you should run using the bioradiomics package. You should extract some features and try to distinguish low-grade gliomas. The cases in this folder here are called LGG from high-grade gliomas, which are the ones in the other folder. And you should try distinguishing the two cases. And you should be able to, and you can try doing that in a different number of ways on different kind of images, because in this data set, as I've mentioned before, we have these two subfolders. Let me show you the data structures, the high grade and the low grade, as I've just said. And in each folder, you have one subfolder for each subject. And in this subfolder, you have 4 images in the nifty file format, which you will read using the nibabel library. And you have 5 images. These 5 images are the 4 MR sequences that I've mentioned you before in the slides, and the ground truth segmentation. And the file names are fixed for each subject. So let me open the notebook myself. Okay, I guess should be relatively well described. Mentioned you have the nifty images. Nifty images are a very common kind of neuroscience format used for research only. It's not clinical because it doesn't save as many metadata. In the first task, you will read the images and display them, and displays with the segmentation superimposed. And the only issue is that you need to pip install Radiomics, and probably it's better if you create a separate environment for that. And well, that's it. Let me know if you have any issues. The first task is just to display the images and display the segmentation superimposed, so it should be relatively quick. Let me know when you get there.